Okay, off we go. So, new location. Much better already. I'm already not warm. Right. Yeah, I haven't taught in that room in such a long time. I had no idea that it actually was getting warm like that. So that was surprise for me. Okay, picking up. Now, one thing you'll notice in this room, there is no sort of like raised desk, and there is currently no podium. And I need the laptop, obviously, and I can't reach it if I stand. So I'm going to have to sit today. So it feels a little weird. But
just drag the podium over from that room. No?
It doesn't have a podium. It has like a desk, and that desk is actually fixed to the ground. Yeah. So I'm going to talk to somebody about finding one. But anyway, for the moment, this will be fine. Okay, so picking up with section 1.3, now you're going to notice that there's a certain amount of this. Just a reminder, I mean, this is going to be, again, peppered throughout the course. That there's going to be stuff that mostly y'all are going to read for yourselves. Again, in the tough decisions, choices of, what can I spend class time talking about? The precious little, insufficient, frankly, class time that we have to talk about the big ideas of the course. What makes the cut? What's most worthy of class time? And this right here, of course, is a review. I mean, y'all have seen this from linear algebra. It's one of the fundamental constructions of linear algebra. And so, I'm going to remind y'all to, remind yourselves, review all of that stuff. And don't forget, for whatever it's worth, this is the model for the more general construction of inner products. So that's another good thing to make sure that you're comfortable with. Although in this class, this is the only inner product that we will work with. Okay. All righty. Now, I do want to say some things about these terms, perpendicular and orthogonal. What do these terms mean? Well, ultimately, definitions are arbitrary, and so different people make different choices in how to define these. Slightly, ever so slightly different. I have actually some pretty strong feelings about this, and it stems from the fact that there are two distinct ideas that we need to describe in relation to, the general concept that these words refer to. One of them is geometric, one of them is algebraic, and they're not the same. Now, this is commonly misunderstood, right? So there's this geometric idea, first of all, the idea of having two directions where the angle between those two directions is a right angle. Now, let's just listen to what I said, direction, angle, right? That's all intrinsically geometric stuff, right? Purely geometric concept of two directions being perpendicular to each other. I said the word. Two directions having an angle between them that is a right angle. Purely geometric. On the other hand, there is this purely algebraic idea here where the dot product is zero. I mean, dot product's an algebraic construction. Equals is an algebraic concept, right? Zero is an algebraic object. So these two ideas are not simultaneous. Right? One of them only applies to non-zero vectors. You can't talk about two directions if there is no direction for one of them. Right? The zero vector does not define a direction. So there is no notion of being perpendicular to the zero vector. It doesn't make any sense. Right? On the other hand, this idea here, this algebraic idea, dot product is zero. Okay, if one of the vectors is zero, sure, whatever. It's still algebra. You can still punch it up. You can still see if it's zero or not. So we have here two distinct ideas. And my fairly strongly felt opinion is that if you have two importantly distinct, close enough to be confused, but importantly different from each other nevertheless, ideas, and if you have two words with which to describe these two different ideas, maybe pick one to use for one and the other to use for the other. Seems like a natural choice to me, right? So, unfortunately, this is not rare, right? Our book does it. And our book is not the only guilty party that will use these terms kind of interchangeably. I think that's unfortunate. Now, don't get me wrong. I was also not brought up right in this sense. I have habits that I'm still trying to get rid of from when I was y'all's age, learning about this material for the first time. And I will sometimes sloppily say one when I mean the other. And I will always feel bad about that and apologize for it if I notice myself doing it. I want to encourage y'all to start right on this process. And if you mean to include the possibility of zero vectors, right, say orthogonal. And if you wish to refer to the geometric idea that unavoidably must exclude zero vectors, then say perpendicular. Right? And we want to keep these distinct because they are different. They mean different things. Okay, let me pause on that. It's a little bit of a subtle idea. I want to make sure everybody's happy. Is everybody happy with that? Okay. All right. Okay, a lot of the rest of this is pretty readable. Now, as usual, when I encounter stuff like this, I always feel the need to say maybe a little something. So I am going to say a little bit about some of what I have in this box. This construction is very straightforward. It's the unique unit vector pointing in the same direction as your given vector v. It's a lovely construction. We use it a lot. It's very important, very fundamental. Make sure you are good to go with this. You might think to yourself how you would prove that this vector has the desired property, something to think through. But it's not hard to prove. It's a matter of taking the magnitude of this construction and just work it out. Use properties of the magnitude operation and just confirm that sure enough this has magnitude 1. Component is a little bit of a subtle idea. Here's the picture. If you have a vector v, this vector v defines a direction. And if you want to know what is the component of some other vector w, like so, the big idea then, before we get into the details, is look, I've got this vector w. It's got a certain amount of length to it, I suppose, but I don't really care about the length of w. When I say component, what I'm interested in is just the part that points in the direction defined by this, direction vector v. Right? I don't care about any of the other stuff. How far is it perpendicular to v? Don't care. Right? We just want to know just in the direction of v, what are we talking about? So my favorite metaphor for this, if you know the game of football, if the ball starts, let's say, I'll use orange, it's the closest thing I have to the color of a football. The ball starts there, and if the ball ends here, how many yards did you gain by this play? Well, you didn't gain this many yards. That's just not how it works, right? You can't just go sideways and call that a gain. That's not football, right? You gained this many yards. And this is called the component. Are we on board? Okay. So notice it can be negative. As in football, you can get, caught for a loss. Components can be negative. They're kind of like coordinates, frankly. If you think about coordinates, let me just get where I have some, where do I have some space? I'll zoom in here. If you think about coordinates, right, if we've got an XY coordinate system here, coordinates could be negative, right? Coordinates aren't distances. If you have a point there, the X coordinate is negative. It's tempting. It's a common mistake to refer to coordinates as being distances. They can't be distances. Distances are intrinsically positive things. There's no such thing as a negative distance, right? So coordinates are a little bit different. They relate to distances. The absolute value is a distance, but coordinates themselves could be negative, which allows us to, it's very convenient for purposes like this. So same thing with, I can't see my own screen. Yeah, there we go. Same thing with components. Components are kind of like coordinates. They can be negative. Okay, this algebra here is pretty straightforward. This is what I'm going to let you read on your own. It's just a matter of observing the trigonometry of basically this triangle right here. That triangle, do some trig, you get this. And then playing around with algebra, I do a slick move here where I both multiply and divide by the same thing. Perfectly legal, right? Perfectly legal. A little bit of a weird choice, but perfectly legal. And then when I do that, what's nice, what makes this a slick move is that becomes recognizably the dot product, which again, y'all are going to remind yourselves of the details of how dot products work. One of the fundamental properties is this right here. Okay. All right. So handy dandy formula for how to compute components is right there. And I like to rewrite this a little bit, capitalizing on what we saw previously. This thing being as it is the unit vector that points in the direction that we're talking about in the first place, you get this really nice little summary down here. Components are dot products with unit vectors. And I like it when stuff rolls off the tongue nicely. Right? I think it's a really compact and efficient way to think about this formula. It's just very pithy. It's just perfect little summary. Components are dot products with unit vectors. Okay. All right. Now, another idea that y'all are going to mostly read on your own, but I'll, as usual, say a couple words, is this idea of a projection. Now, you're going to notice very quickly this picture that I drew for a projection. It looks just like the picture we drew over here for component. And this is a very closely related idea. The big difference between projection and component is what kind of critters they are. Components are scalars. They're kind of like coordinates, right? They're just numbers. Projections are not. Projections are vectors. It's basically the vector it's the vector version of the component, you might say. Okay. So that makes the relationship to components really easy to write down. After all, this projection vector, right? We know what direction it points. It points in the direction of the unit vector. That's the direction. We also know what the magnitude is. The magnitude is by the way, wrong color. But I'm deliberately misspeaking here. I will correct my little math crime momentarily. But I'm going to say the magnitude is the component. And why I have to correct myself there, my little math crime is, I said magnitude. Well, magnitudes are intrinsically positive things. So this isn't really a magnitude exactly. This is, it's a component. It could be negative, right? But still, it is the correct scalar. It's the scalar that I'd want to multiply by, because after all, I do want it to be possible to be negative, because if we're talking about a vector that's kind of going the wrong way, I want to allow for the possibility that the projection would be also kind of going the wrong way, as it were. Okay. All right. So there you go. Now there's some ensuing algebra, and again, I'm going to let y'all read through this algebra. It's pretty straightforward. Make sure you can do this. Make sure you can follow along there. You will notice that it leads you to a choice between two different formulas for thinking about how to compute projection. You can compute projections with this formula, or you can compute with this formula. And I want to try to make an appeal here. I think this is a perfect opportunity to remind you of how to make decisions about this choice. Which one of these looks better? Now, the tempting choice is to say, look, if you want to compute a projection, we're given two vectors, v and w. Those are what we're given. And check it out. This is all in terms of v's and w's down here. And in terms of plug and chug, it's hard to beat this for convenient. It shows you exactly what to plug into where. Isn't that alluring? And a lot of students gravitate toward this formula down here at the bottom. And I think that's a mistake. Yeah, look, it's a correct formula. That's true. Okay. But you got to remind yourself, can be hard to remember this. The fact that this is best for plugging and chugging shouldn't matter much in a course that isn't really about plugging and chugging, right? It's the right tool for the wrong job in some sense here, right? So I'd like to make the pitch for this being the much better formula. Yeah, sure, there's the additional inconvenience of you got to compute what the u vector is first, right? But this is more naturally connected to the picture. This is easier to remember. It's easier to understand. It's easier to explain to someone else why you would care about this formula. Because it, again, just naturally connects to this picture right here. It's like, well, why do I want to do this? Okay, well, I want to do that because that is the direction that we're pointing in, and the appropriate scalar, namely the component, is what we're computing there. Everything that happens in this formula makes sense in the picture. That's what we do here. Right? That's what this class is about, is understanding concepts, being able to relate ideas to other ideas, be able to make connections. Right? So this formula is better for what we're going to be doing. Right? Yeah. Mm-hmm.
If the V was in the opposite direction, then would the projection of W be on the span of V, like the same one? Or
yeah. So sure. So let's entertain that question. So if I understood you correctly, you're saying that maybe what if V points this way?
Yeah.
Okay, and just to avoid the confusion, let me kind of get rid of this then, and of course U no longer like that. And so let's ask ourselves, okay, in the direction defined by V, what's the projection of W? Well, again, the big idea is still that we want to drop the perpendicular, right? And we're interested in, when we say the projection, we're interested in this vector. Oh, I can't use that color. I've already used that color. We're interested in this vector. That sort of is the vector version of the component. You can see it's still exactly the same thing, right? So which direction V points, look, V's job is to kind of define a direction, and really that's all. And, how W projects to that line, we're still projecting the same W, it's still projecting down to the same line, so we do still get the same answer. Is that satisfying?
Yeah.
Okay. Everybody else all right with that? Okay. Yeah, good question. Good stuff. Whoops. There we go. Okay. So try to persuade yourself, I would suggest, that you should gravitate more towards formulas like this that connect to ideas, and I don't want to say ignore stuff like this down here, and just to correct myself, it's not that we will never do any plug and chug. Well, of course you're going to be doing plenty of plug and chug in this class, right? But it's going to be plug and chug that comes after having dealt with ideas and connected ideas, and that's the hard part, is the connecting the ideas. And the plug and chug at the end, yeah, you do have to be able to plug and chug at the end, but it's just not the only thing we're doing. Yes?
So in the first formula, when
Yep.
you said the component's not really an magnitude, can you call it a scalar?
Yeah, absolutely. Scalar is a great word for it. Yeah. Yep, indeed. Scalars are allowed to be negative, absolutely. All right. Is everybody happy?
Also, in the picture you just drew, like when V was in the opposite direction,
Yeah.
what would be the component?
So the component there would be negative. Yeah, here, let me flip back to it. I think I can do this. There we go. Okay. Yeah, so the component's negative because when you drop this perpendicular, it's not going in the direction that V is going. So yeah, if you were to take the formula on the previous page in a case like this and compute the component, it would be negative. You'll also find that the unit vector U would be that way, And so then, when you take this formula down here, U is pointing in the opposite direction of previously. The component is negative instead of positive, and that's why, from an arithmetic point of view, why you get the same projection vector. Yeah. Okay, good deal. All right, let's see. Now there we go. Okay, so, real quick reference. Sometimes there are proofs in plane geometry, stuff that you probably would have seen in a high school geometry class, that are very nicely streamlined by vector algebra. And there's a couple of examples on the homework. This, again, tough choices and all that. I wish I could spend time on everything, and this doesn't quite, make the mark. So take a look at those examples in the book of how they use, vector addition and vector subtraction, etc., to prove some cool old facts from plane geometry. And then now there's a couple of homework exercises where you'll do sort of similarly. Okay. All right. Okay, new topic. This is a big one. There's some really mysteriously connected ideas involving cross products and determinants and certain geometric ideas that are kind of hard to explain in advance. But anyway, so we're gonna talk about all these various connections between these various ideas. Ultimately, cross products and determinants are very sophisticated concepts. I know y'all have seen determinant before. It gets brought up in linear algebra class. The focus in a linear algebra class is going to be properties of determinant that are most useful for linear algebra, which is not the same as what's most useful about determinants for multivariable calculus, right? So we're going to see some different sides of determinant, and we're going to see some, I don't know what y'all may or may not have done with cross products previously, but we're probably, if you've seen cross products before, we'll probably have a different focus than what you've seen also. Okay, I like to start with these geometric ideas. This following is not in the book, but it's the perfect segue to something that is, and it's very important. So I'm going to talk about when you have two vectors, specifically an ordered list of two vectors. So the order matters. When I say A and B, I don't mean the set of vectors A and B. Kind of two vectors, whatever. I named them in alphabetical order for no reason, but it doesn't matter. No, I mean the ordered list. A is importantly first. Whoops, I missed. A is first. B is importantly second. That's what we mean by an ordered list. And these vectors, they point in directions. And I want to talk about the relationship between those directions, right? And in particular, if we were to look at, let's suppose that we look at this situation right here, where our first vector, A, is that way, and let me just do this. Let me just say, there you go, 1. And our second vector, B, is that way. If you think about it, in that order, A being first, B being second, right? Green to blue, as I have it sort of color-coded here, green to blue is unavoidably counterclockwise. Everybody see what I'm talking about? And when I say counterclockwise, what I mean is, if you look at the direction, from the A direction to the B direction, what is the kind of the most direct way to get from the A direction to the B direction? The closest way to rotate is counterclockwise. Is everybody on board with that? Okay. All right. Now that's just because that's how those vectors happen to lay out. Now let's entertain a perfectly reasonable different possibility. Let's suppose that A is that, which it could be, right? Whatever. B maybe is that vector like that. Now what would I say about this ordered list? Right? Again, from A to B, from the green direction to the blue direction. Well, now that's kind kind of really ought to call that clockwise. Everybody see what I'm saying? Right? So depending on what your vectors are, when you write down an ordered list, generically, typically, it makes natural sense to call that list, again, not the set, right? But the ordered list, clockwise or counterclockwise, depending on which directions they point. Now, there are some anomalous, annoying sort of, like we could have something like this, in which my first vector is like so, and then the second vector is, same direction. Would I call that clockwise or counterclockwise? It's kind of neither, right? It just doesn't make any sense. So these kind of anomalous, annoying third possibilities, there's various versions of these, right? So here, the reason we can't talk clockwise or counterclockwise is because they point in the same direction. Likewise, if they point in exact opposite directions. Likewise, if one of them is the zero vector and doesn't have a direction, right? Various annoying possibilities that don't really fit into the whole clockwise, counterclockwise thing. And what you can convince yourself of, and I think this is a nice little exercise to think through all the different ways that we couldn't say clockwise or counterclockwise. Think about all the different ways that a pair of vectors might be linearly dependent, and notice they're exactly the same cases. It's a good little process to go think about all these different versions and persuade yourself that they're the same. Okay, so these are the three possibilities. When you have an ordered list of two vectors in the plane, very importantly, in R2, in the plane, these are your three possibilities. Okay, now, who cares? Well, just to try to pique your interest, there are some pretty natural properties to these ideas. So for one thing, they're mirror images of each other, right? So if I have, for example, if I have a vector and then a second vector, and if that is, as I have it drawn here, counterclockwise, right? If I look at their reflections, the reflection of A first, and then the reflection of B second. And if I ask what order is this list, well, it's, again, green to blue. Now it's clockwise. Right, so now just to streamline, I think it's believable, it's natural to refer to this, what we've described here in detail, as saying that the clockwise and counterclockwise are mirror images of each other, they're reflections of each other. And I think that's, again, a kind of a pithy and convenient way to say that. So along those same lines, another natural property, if you trade the positions in the list, so notice if I put the A where the B was and put the B where the A was, like so, then what had been counterclockwise, right, becomes, color choices, clockwise. So nice, another little natural property to keep in mind when you trade the positions of those two vectors, that changes the order. So reflecting changes the order. Trading positions in the list changes the order. And then lastly, I'm going to say independent of rotation. So if you have, and let me just hand gesture for this, if you have a pair of vectors A, B, and as I have them drawn there, they're counterclockwise. If I rotate, right, if I rotate both vectors, I rotate the pair, it's still counterclockwise. Right? So I can take a clock off of the wall, and if I angle the clock, it still goes the same clockwise direction, right? Nothing really happened. All right, so who cares? Again, well, this is a nice segue into a more sophisticated concept, and that is the three-dimensional version of this. So instead of having two vectors, now if I have an ordered list of three vectors, now in 3 dimensions instead of 2 dimensions, is there kind of a sort of a clockwise, counterclockwise thing. Analogous. It's not going to be the same, obviously, but is there something kind of like that? And it turns out that, yeah, there's a great answer to this question, and it involves the human hand. This is just a convenient tool for describing this idea. But what we mean by a right-handed list. And now this is gonna involve some physical demonstrations. So again, I'm gonna have to come up here and sort of do it in front of the screen. So we'll start with right-handed. Use your right hand. Very important, your right hand. Right. We use the index finger for the first vector. The rule is that you have to keep your index finger parallel to your palm. Right. So like that. Point that index finger in the direction of the first vector in the list. First vector in this list is A, so there you go. Next, having done that, we're going to use the middle finger next. Now, the rule for the middle finger is that it can only bend in the direction that middle fingers want to bend. Don't, right? No contortion moves like that, right? So, we're going to try to figure out a way to bend our middle finger in such a way that it'll point in the direction of the second vector. Now, that's set up pretty conveniently here, and I can just do it like that. Right, so I'm bending my middle finger the way middle fingers want to bend. Is that cool? Everybody with me? All right. Now, at this point, these first two vectors, you'll notice define a plane. Okay, so there's this plane here that's defined by those first two vectors. Notice that the thumb of my right hand points on what I'm going to call one side of that plane. Right? So, now again, no cheating, right? No funny business. Right? So, pointing the thumb the way thumbs want to point, that defines a well-defined side of the plane. And notice this third vector, C, is pointing on the same side of the plane. It's pointing up. Okay, so that's on the same side of the plane. And so my thumb doesn't have to be able to point in the same direction as C. It just has to point on the same side of the plane as C. And so this is a right-handed list. Everybody on board? All right. Now, if the vectors were laid out like this, now notice this is kind of similar looking, but now notice the A and the B is different vectors, right? So it's not the same. It's still ABC, but now we're interested in the vectors if they were geometrically like this. You cannot do this with the right hand. We can try, and it's a healthy exercise to try and fail. Okay, so index finger in the direction of the first vector. Keep in mind, first vector A happens to be pointing that way. Second vector B, middle finger and all that. Wait a minute, I'm not allowed to do this move, but I can twist. And now notice I'm still pointing my index finger in the direction of the first vector A. Now I have my middle finger pointing in the direction of the second vector B. So I can do the A and the B. Now notice though my thumb is pointing on the downside of the plane. C is pointing on the upside of the plane. This is not a right-handed list because it doesn't work with my right hand. It totally works with my left hand. Yeah? Okay, so this is what we would call a left. This list for these vectors is a left-handed order. Okay. So, and again, there's various cases where it just it's neither, right? And again, I think it's a really healthy exercise to think through all the various different versions by which this could fail, and it's neither right nor left-handed. And you're going to notice again, in a wonderful coincidence, that it lines up perfectly with cases where that list of vectors is linearly dependent. Okay. All right. So what's cool about this relationship, if you look at this clockwise, counterclockwise, you look at this right-handed, left-handed, they've got all the same properties. They're mirror images of each other, right? Right and left hands right and left hands are mirror images of each other. Right? Secondly, you trade positions of two vectors in the list. Okay, well, same thing here. Now this is an exercise, and y'all should think through the various different versions of this. Here, I've switched the positions of the first two vectors. Instead of A, B, C, now I have B, A, C. Play the game. You'll find that this list is right-hand order. This list is left-hand order. Think it through, right? Do the hand gestures. And in fact, no matter which two vectors, we could have switched the A and the C. We could have switched the B and the C. Whenever you switch any two of the vectors, it will change the handedness. Yeah.
So do our index figures point at the first vector in the list?
Always.
A?
No. The alphabetical order is so much a who cares. Yeah, no, we're not at all interested in alphabetical order. So when I say B, A, C is left-hand order, again, this is an ordered list. The first vector is B. I could not care less that it's alphabetically second. Does that make sense?
Yeah.
Yeah. So there is, I understand the temptation, right? And worse, there's this temptation to think, well, yeah, but B, it used to be the second one. Yeah, that's ancient history. That's their problem, right over there on that side of the page. We're looking at B, A, C. Whichever one is written first is the first, and that's the index finger. Does that satisfy?
Yeah.
Everybody good? Yeah.
Could you scroll up?
Oh, yeah.
Could you show how the right one is left-handed?
This is left-handed?
Yeah.
Oh, well, let's see here. What did I write? So A, B, C, right-handed. Okay, I just got A, B, C is right-handed. I'm claiming this is left-handed. Okay, so A prime, B prime, C prime.
Oh, okay.
Left hand. Yeah. Is that good?
Yes.
If I try to do it with my right hand, A prime, B prime, my thumb's going the wrong way. Yeah. Yep.
Thank you.
All sorts of fun and games with, persuading yourselves of these properties here. They're mirror images of each other. Trading will always change the order. And then lastly, again, it's sort of rotation independent. And again, pretty obvious, right? If this is my demonstration of this list of vectors being a right-hand order, well, if I rotate everything, it's still my right hand, right? So, again, independent of rotations. Okay, all right, lots to play with. Now, there is a fourth property here, and it depends on how you think about it. I think this is handy, so I like to mention. Technically, this is a special case, or a sort of this is a consequence of property number 2 here. But I'm going to sweep that under the rug. When you cycle, the order doesn't change. So what I mean by cycling is kind of just kind of slide everything over. Let's see here. Let me do it like this. So if I move C to where B was and B to where A was, and A kind of falls off and comes around and goes back to where C was, you just literally kind of rotate everything around, then it doesn't change the order. Now, I heard somebody say, yes, this is in fact 2 trades. And so that's why this works in some sense. But I like to think of this as being a separate fact because this idea of cycling is also kind of natural in its own way. So neat property. Okay. All right. Couple of neat facts about linear algebra. Now, y'all may have seen these in the linear algebra class. You may not have seen these in a linear algebra class. And these take a little bit of setup to describe. So bear with me. A lot to describe here. We're going to talk about a list, an ordered list. But by the way, when I say list, that always means ordered list. Right? I wrote ordered originally, and I said it a few times for emphasis purposes. But list means ordered list. Well, here's the thing. If you have a list of 2 vectors in R2, you can always kind of do this move where whatever vector is first, you make that the first column. Whatever vector is second, you make that the second column. Anytime you have such a list, you can also make a matrix. Anytime you have a matrix, well, that defines a linear transformation. Now, we have this standard construction of this is how we relate a matrix and a linear transformation. So you give me a matrix, now I've got a linear transformation. Nothing's happened yet. I haven't said anything yet. I'm just saying, if you give me a list, notice there is a corresponding matrix, there is a corresponding linear transformation. And then, by the way, I can also say, look, as a default sort of standard, let's always look at the unit square, and I can always ask, if I want to, which I do, what do you get out from this linear transformation when you plug in all the points of the unit square? And appeal to your previous experience with linear transformations. Whatever this linear transformation is, what comes out will always be a parallelogram. So now again, I haven't made a statement yet. I'm still just setting stuff up. But the big takeaway here is when you have a list, you also have a matrix. You also have a linear transformation, and you've also defined a parallelogram. So you've really got 4 objects that are all sort of connected to each other. Yeah.
What is the R?
What is the what now?
The R here.
Oh, this R right here. Is that right? Yeah. This is my little shorthand you may recall from early on, section 1.1 or 1.2, somewhere along there. This is a shorthand for x comma y. So it just refers to whatever x comma y point here that you plug into this linear transformation. This is a form. This is how you multiply the matrix times x comma y. That'll give you your output. Yeah, it's easy to forget that, right? So heads up, be on the lookout. The R vector, another way to say what the purpose of the R vector is it's the position vector for whatever point you're looking at. It's x comma y. Yeah. Good. Everybody good? Again, I haven't made a statement yet. I'm just noticing that these things all connect to each other. Okay, so let's actually make a statement now. The first statement is that if you take that matrix and if you look at the absolute value of the determinant of that matrix, that will give you mysteriously the area of that parallelogram. It's shocking. Very first time I saw this, I thought there's no way this could possibly be correct. Let me try to persuade you that this is nonsense. Which it's not. It's true, right? But let me try to persuade you why this should feel like nonsense. How do we compute areas? Well, we compute areas by dropping a perpendicular, and I've got to compute that height, which I would do with a little trig involving that angle, and then I got to multiply by this distance, which involves a square root. So we've got angles and trig and square roots. I feel like the formula for the area should involve angles and trig and square roots. And I would have you believe that no, it involves 3-function arithmetic. You multiply and then you multiply and then you subtract. Right? You see why I would be suspicious, right? And I was very suspicious about this when I first saw it. How could 3-function arithmetic answer a problem that seems like it's got to involve square roots and trig? It is creepy that this works. But it does. Very powerful fact then, right? And this should be one of the, if you want to try to persuade someone that determinant is powerful magic, this is a pretty good foot in the door on that, right? This is a real eyebrow raiser, I like to call them. Wait, how could this possibly be true? Okay, cool fact about determinant. Okay, let's see here. Moving along. Here's another neat fact, and that is the sign of the determinant. Sign meaning plus or minus, just the mere fact of whether it's a plus or whether it's a minus tells us the order of the original list. It tells us whether that's whether that's clockwise or counterclockwise. In particular, positive means counterclockwise and negative means clockwise. And again, it's like, come on, how could that possibly be? Determinant is this very simple formula involving a couple of multiply and subtract, and it looks like a trivial little formula, and it's somehow getting its hands not only on the question of angle and what directions are these pointing, but it's like it's got built inside of it this intuition for which way do you go. How could it possibly be that simple, right? But it works. So another shocking fact about determinant, seemingly able to accomplish much more sophisticated geometric ideas than it ought to be able to. Okay. All right. Now I do want to pause. Let me clean up my picture. And I want to come and recognize that this picture that I drew, I had to draw something, and I drew A like that, and I drew B like this, because I had to put them somewhere, and in that arrangement, A, B is counterclockwise, and I'm certainly not trying to suggest with this picture that it's always counterclockwise. I had to draw it one way or the other. So let's just play around with the possibility of what if it goes the other way. What if it were like this? What if that was A and that was B? All right. Corresponding to clockwise. And I want to come back here and notice that's a picture then of this sort of second case down here. That's a picture of if the determinant were negative, the list being clockwise, again, as indicated now in that picture. And I want to try to make an appeal now as to what does that tell us about the linear transformation. The linear transformation itself. And there's a really nice observation here. I claim that linear transformation has to kind of flip the plane upside down. And here's the way you see that. How is it that this means I have to flip the plane upside down? Well, keep in mind, let's see here. Do it like this. So A, this vector A is that first column. Don't forget about from linear algebra, the first column is always the image of the first standard basis vector. Right? The first column is what you get when you multiply by 1, 0. You take 1, 0, multiply by this matrix, you get that first column, A1, A2. So green goes to green. And then likewise, the second vector is the second column, and the second column is the image of the second standard basis vector. So green to green and blue to blue. And now geometric appeal. How is it, what does this linear transformation have to do to turn, let's see how to do this. Let me do it with my index finger for the first vector, thumb for the second vector, right? How am I going to turn green and blue here into what we see there? And you can talk about, stretching or rotating, various different things you might do, but somewhere along the line, you're going to have to flip, right? Palm up is going to have to go to palm down to make that happen. So there is a flipping of sorts. Is that cool? Right. So I think that's a nice way to think about this as well. Now, it means the same thing as saying that the list AB is clockwise, right? But there is, I think, an important difference. When we make a statement about the list being clockwise, there's something kind of static about that. It just is. That's just where they are. The vectors are just sitting there. Here, we're making sort of an active statement. We're describing how a function works, what a function is doing. That function is literally flipping things upside down. And thinking of this equivalent statement in terms of the transformation, not the parallelogram result, has some powerful features to it. Okay, all right. So that's just kind of an equivalent formulation. If I can get this to cooperate, here we go. Okay. All right. So yeah, really cool facts. Determinant, its magnitude tells you the area, and its sign, well, it tells you about the order of the list. It tells you about the kind of does the transformation flip things upside down? Well, I call it inversion there, etc. Oh, of course, there's this third annoying possibility to determine it could be 0, and that, not surprisingly, gives you the third possibility of dependence. And geometrically, I think it's a nice exercise. Think it through. Persuade yourself that means that the transformation has a squish in it. Using some linear algebra talk, it means that the linear transformation is singular. The linear transformation has a null space. The matrix row reduced would have only one, at most one pivot. Various different ways that you can say that. Anyway, again, think that through. Nice exercise. Okay. All right. So cool facts about two-dimensional determinants. And notice how this theorem looks on the page. And now I'm going to scroll down and notice how this theorem looks on the page. Notice how it looks really, really similar. I deliberately laid out this second theorem on the page exactly the same layout because it's morally the same idea. Again, we have a list that we use to make a matrix, that we use to define a transformation, that we use to create a geometric object. But now that we're in 3 dimensions, it's a list of 3 vectors. That gives me a 3x3 matrix. That gives me a parallelepiped. Right? So everything's 1 dimension up. Right? But morally, kind of the same ideas hold. Determinant of that tells me how big that is. Naturally, being 3-dimensional, volume, not area. But still, the absolute value of the determinant tells us how big the thing is. Just like in 2 dimensions, the absolute value of that determinant tells us how much area that has. It's very much a 3-dimensional version of the same theorem. And likewise on down the road. So in particular, plus or minus in the determinant tells us right hand versus left hand for the list. And likewise, now it's a little bit harder to kind of think through the geometry, but let me just do a little hand waving down here. If I have a right-handed, E1, E2, E3, IJK, right, standard basis vectors, right-handed order, I can talk about rotations and magnifications, but right hands stay right hands unless you do like a mirror image reflection to make a left hand. So a negative determinant, meaning a left-handed order here versus a right-handed order there, what does the transformation have to do to turn a right hand into a left hand? It's got to have a reflection in it. Same basic idea. All right. Okay. All right. So, yeah, go ahead.
What do you mean by all orders reversed?
Yeah. So, orders reversed means that if I had a list of vectors here that are right-handed, their images would be left-handed. And if I had a list over here that was left-handed, for whatever, a couple of, 3 vectors and a left-handed list, their images would be right-handed. And whatever, if this determinant is negative, then whatever handedness you have in the domain, you would have the opposite handedness in the target. Yep.
When laying out the 3 vectors, can we start out with a left-handed orientation versus a right-handed orientation? It would take 2 different start out from 2 different places, and then end up on the same place there.
No. So if you, let's say you have 2 lists over here, you have a left-handed list and a right-handed list over here. The left-handed one will turn into a right. We're assuming we have a negative determinant, right? Left goes to right, and right goes to left. So different handedness here goes to different, sort of reversed, but still different in the outputs. Everybody good? Yeah. Mm-hmm.
So when you order, you're meaning like the right hand?
Yeah, that's the whole right hand, left hand thing. Yeah, absolutely. Yeah. Okay, it's kind of mysterious how determinant gets just kind of all over this. We're talking about so much geometric stuff, right? We're talking about volume, we're talking about handedness, we're talking about reflections. Determinant, boom, just gets right on it. The absolute value of the determinant tells you that volume. The sign tells you about the handedness and the inversions, the reflections. And again, this mysterious formula where you go across the top row and you multiply that times, and you look at the sub-matrix, and you remember all the formulas for determinant from linear algebra, and it's this oddly arbitrary, weird, creepy formula that seems to be just kind of made up nonsense, but oh my God, it's so powerfully connected to geometry. All right, so cool stuff. Moving along. Now, I do want to say a quick word about this. The book presents the following ideas in a different way. Most books have their own way of presenting these following ideas. I have my own point of view on how to present these ideas. There's pros and cons with any such choice. I've picked a presentation that I think gives the maximum focus to pictures and concepts. The dirty little secret, the downside of my presentation is that, I'm never really quite going to prove the results that I'm claiming. The way I sweep that under the rug is, you'll notice I didn't prove this big theorem here. I'm not going to prove it. I'm just going to assert it. And, you should be a little bit suspicious of that choice, right? How do you know I'm not making some nonsensical claim? Maybe I'm putting one over on you. Don't trust me, right? Mathematicians don't trust, right? So I apologize for that. It's there's pros and cons, and don't get me wrong, we could prove these results. It's just that I know 2 ways to prove these results. One is extremely tedious and not instructive at all. And the other is sophisticated in a way that I think makes it not quite appropriate for this course. This not being really a course about proofs anyway, I'm just not going to do that proof. So anyway, heads up, the order that I'll present these ideas is a little different, actually quite different from what the book does, but I think you're going to like mine better, frankly. But by all means, look at what the book does, make up your own mind on that. Okay. All right, so here's a definition of this thing called the cross product. Let me not start with that. I want to start with this down here. Determinant. We've already seen how the determinant is a natural thing. So determinant, powerfully natural, cool ways, right? And that's going to be my starting point. Now, how do you compute determinant? You go across the top row and you play the usual game. I don't know if you've ever thought about the following before, but when you go across that top row, You're going to take this and multiply it by something, and then you're going to take that and multiply it by something, and then you're going to take that and multiply it by something, and then you're going to do this plus minus plus thing. You're basically multiplying and then adding. You're doing a dot product of that top row with other things. That's the first observation I want to make. Determinants are dot products. Again, it's kind of a weird way to think about it, but sure enough, determinants are dot products. Okay, well, now wait a second. Again, we've agreed that determinant is powerfully natural, geometrically natural. And I think y'all have already been persuaded long ago that dot products are powerfully natural.
What do you mean by natural?
I just mean that it's a reasonable thing to write. It has immediate connections to obvious pictures that you can draw and things like that. So when I say dot product is natural, for example, dot products relate to magnitudes and angles, right? It has immediate connections to geometrically simple things. Now, not every formula you can write down has this feature, right? So, for example, if I get crazy formula that we will never make any use of, but just for sort of explanatory purpose. What if I say I'm going to define something called the Bray product? Okay, and the Bray product of two matrices is that you take all the elements of both matrices and you just multiply all those numbers. Okay, it's a free country. You can define whatever you want. And if I were to say I'm going to define that, I'm going to call that the Bray product, a reasonable retort would be, yeah, that's unnatural. How does that connect to geometry? It doesn't. It's a bunch of nonsense. It's a poor idea. You see what I'm saying?
Yeah.
Dot product is not like that. Dot product makes sense. It connects to magnitudes. It connects to angles. You get what I'm? Yeah.
Dot product geometrically was about components and.
For example, that's on the list of cool natural connections that we can do with dot product. So that's all I mean by natural. It's a great question. It has immediate connections to fundamentally simple geometric things. Yeah. Okay, so determinant is natural, dot product is natural, and I'll tell you what, I think it means that one way or the other, I was trying to switch colors, one way or the other, then this, whatever that is, I mean, it's the thing that connects the natural idea of dot products to the natural idea of determinants. So this thing here, whatever it is, it is highly suspicious that this might be worth looking at. We don't know, but it might be somehow geometrically natural. So that's going to be my motivation for why I'm going to call this thing, I'm going to call it the cross product of A and B. Simply suspicious because of how closely it fits in with determinants and dot products. Okay, so thus rewriting down here, again, we made the observation that we're talking about dot product with C, right? And this thing then, if I call that a cross product, then altogether I have a nice way to reconsider what determinant is, and that is it's a product of sorts. That's what we call a triple product. That's just a different way to think about determinants. And by the way, it doesn't mean anything new. Triple product literally means determinant of that 3x3 matrix. Yeah.
So are you essentially saying like the top row like acts as a standard basis?
Oh, you're talking about this up here? Okay, we'll get to that in a second. Yeah, I haven't gotten to that yet. Yeah. Okay. All right, so this is called a triple product. Again, it's just kind of it's just an alternative way to think about determinants, 3x3 determinants. And so now let me get to what you asked about. Why did I write this like this? It's arguably, depending on how you look at it, kind of a coincidence. But if you were hypothetically to write down this kind of nonsense right here. I mean, let's get the ugly part out of the way. I've written this down like it's a matrix, but shouldn't a matrix have elements that are numbers? Am I allowed to have an element of a matrix be a vector? No, golly, uncomfortable, right? So I'm going to call this a symbolic matrix. Let's ignore the fact that it's kind of nonsense. Just, forgive me, right? Play along. This symbolic matrix, if I were to ignore the fact that it's nonsense, if I were to take the determinant using the usual formula and just kind of crank it out, going across the top row, blah, blah, son of a gun, you would get exactly this thing that I've already decided I want to call the cross product. So this is what I'm going to call a memory tool, right? It arguably doesn't really quite mean anything, but it's a very handy little memory tool because this little formula is hard to remember. There's so many this times that, and there's the minus, and if you get them backwards, then it's easy to, oh my God, it's so easy to mess this up. Please don't memorize this formula. Don't even try. It's not that you can't do it. Of course you can, but you can also mess it up, right? And the goal is not to memorize it at some point. The goal is to have an understanding of it that you'll be able to remember forever. And this is a lot more organized and easy to keep track of, much easier to remember. And in my life, I have never memorized that formula, ever. Just use this. It does the bookkeeping for you. It's nice and organized. You've already memorized how to do determinants. Let that, you kind of piggyback off of that, and that'll keep track of all the pluses and minuses for you. So this is the formula. Let me get back over to this. When I think about cross products from a computational formula point of view, this is how I do it. And I, again, never in my entire life have I memorized that, and I never will. Yeah.
Just to confirm, what's E1, E2? Like, how does that disappear when you do the determinant?
Yeah. Okay. Well, right. So so this gets multiplied by the determinant of that little submatrix, right? And so that gives me A2B3 minus A3B2 times 100. Right? Because the E1 is 100, right? And so that gives you this comma 0 comma 0. Right? And then as you proceed, it keeps kind of giving you the correct coordinates. Yeah. Right. Yeah.
Why don't you just use 1, 1, and 1? Why use
because then you'd get a scalar. And keep in mind, what we've decided, this is the object of natural interest. Right? This is what we want to reproduce. It's fundamentally a vector. It's not a scalar. It's got to be a vector.
Okay.
See what I'm saying? I need to be able to dot product with it. Yeah. So it's got to be a vector, and this is the crazy nonsense that you have to do in order to make a determinant, air quotes, determinant produce a vector. Yeah.
Will we ever use like IJK for the
Yeah, IJK is an alternative notation. I mean, my problem with IJK is that it is you start running out of letters eventually, and remember, this idea that 3 dimensions is enough is silly business that doesn't deserve the time of day, right? And we should be prepared for dealing with more than 3 dimensions. We're not going to draw any pictures, right? I mean, don't worry, I'm not going to. That's not even possible, right? But we should be prepared when we write down formulas to deal with more than 3 dimensions, and IJK isn't good at that. But E1, E2, E3, E4, E5, E6, E7, very, very convenient. Is that satisfying?
Yeah.
Yeah. Okay. So there's a long list of properties here, and I'm sorry. Go ahead.
I have a question. So you have the E on the top. Is that what you're technically saying at the bottom, and the E becomes
The what now?
so like the E's?
Yeah, the E's kind of become C's in a way. Yeah, I mean that's a nice pattern to notice. I would urge against looking for too much meaning there. right? But it is a nice little pattern to notice, and then you should, of course, think about what happens when you multiply out this dot product, and then think about what happens when you write down this determinant. You're going to notice you're writing down a lot of the same stuff, right? But it's really just kind of a pattern. I'm not literally replacing numbers with vectors. That's just kind of coincidentally how the pattern tends to work out. It's a good observation. But I think I don't think there's much of a payoff down that road. Yeah. Okay. There are some wonderful geometric arguments to be made to understand properties of dot products and cross products and determinants and stuff like this. And I'm sad to say I've had to give up on rationalizing how it's worth class time to actually talk about those. When I spend time talking about like this proof right here, for example, it's a wonderful proof. It's very cool. There's a lot of cool geometric ideas in there, and it's stuff that I think y'all can benefit from looking at and thinking about. But this isn't really a class about proofs, and cross product is more of a means to an end, really, in this course. If this were a linear algebra course, I'd probably have a different opinion. But I've had to sort of give up. I mean, as much as I enjoy talking about these super cool geometric proofs, it doesn't really quite make the cut. So you don't have to look at these proofs. I can't really justify it. But it is good background. It will be helpful to you as you're trying to sort of digest these ideas. So I encourage you to look at these proofs. But you don't have to. It's not going to. The facts will be on the test. Yeah. Fair game. The proofs that I have outlined here will not be. So you don't have to. So anyway, long list of properties, and this is just a matter of looking at them. So in the remaining 3 minutes, I'm just going to kind of doff the cap to, hey, cool facts. This theorem here says that when you take a cross product, the result is orthogonal to both your input vectors. That is super cool. Now, why is that true? Well, you can prove it in a couple different ways. I mean, if you want to prove orthogonality, one way to prove orthogonality is to compute the dot product and confirm you get 0. So you can just straight up punch up the algebra. There's really not that much to it. You just write it down and boom, there it is. You can also make cool arguments like so, geometrically instead of algebraically. Again, I think that's helpful and, good exercise. Look at that if you'd like, but do make sure that you know the result. Cross products are orthogonal to both inputs. Likewise, when you cycle triple products, you don't change the value of the triple product. Likewise, the magnitude of a cross product gives you the area of the corresponding parallelogram. Super cool fact. And another one of these, what are the odds? How could that be? Cross product got defined in terms of connection between dot products and determinants. How are we getting a parallelogram? Aren't we in 3 dimensions here? Why shouldn't it be a parallelepiped? It feels like. But no, if you have 2 vectors A and B, and you look at the parallelogram, the area is the magnitude of the cross product. Very surprising fact, and a lovely proof. Again, not required, not on the test. You don't have to know it, but I think you might find it a useful exercise. Cross product being 0 kind of says that those 2 vectors must be parallel, but of course parallel implies directions, directions implies non-zero, and these don't have to be non-zero. So the better way to say this is when the cross product is 0, the list is dependent. Yeah.
Wait, sorry.
Yeah.
So the triple product, is that literally just the determinant?
Yep.
Like matrix A, B, C itself?
It's literally the definition of triple. Okay, the slight distinction. The sloppy version of the statement is that triple product is determinant.
But then,
the fine distinction is that determinant is something we do to a matrix. Triple product is something we do to a list of 3 vectors. And yeah, technically, if you have a list of 3 vectors, you can make a matrix, but they're nevertheless technically different things. That's the only difference. Yeah. Yes.
But you order them like C1, C2, C3. So, but if you do order a list of 3 vectors as a matrix, it will be A1, A2. So
well, you got to use the order matters, and so you do have to preserve the order. You'll notice that I put C first there. So first entry is the first row. By the way, of course, transposes don't matter, so you can say rows or columns. I'm using rows here, right? But yeah, first to first, second to second, third to third, and that you do have to be careful about. And if you get them in the wrong order, you might have a minus sign because of the switches. Yeah, right. Okay, so mostly I think what I'm going to do is let y'all read the rest of these properties. So we've talked through most of them already. Again, you don't have to look at the proofs, but there's a neat fact that this specific list here, where you take 2 vectors and then follow up with the cross product, that will never be left-hand order. It's always right-hand order, or it could be dependent, annoying little anomalous possibility. Basically, it's always right-hand order. That, A, B, cross, always right-hand order, except for the, 0 possibility. And let's see here. There's a sort of 2 seconds. There's a kind of reverse commutativity here, anti-commutativity. Don't make the mistake of thinking that all multiplications are commutative. They're not. This one is anti-commutative. And there's also sort of a linearity of sorts, and I think this is a good thing. Y'all can read this for yourselves. I'm calling this a linearity because cross product of a combination is the combination of individual cross products, just like linearity. Okay, let's see here. And this up here is non-critical. Give it a glance, but it's nothing to worry about too much. And I'm going to call us done with this page right here. You can read the rest. I'm sorry. So I'm noticing I'm over time. So let me call it here, and then if y'all have questions, I'll stick around for a minute to answer last questions. Okay. Good to see y'all. See you tomorrow. Oh, and don't forget, while we're here, don't forget homework due tonight. Right. So hopefully you've already started on the homework that we assigned yesterday. Right? Hopefully you got much of it done. Don't forget, I'm going to office hours in just a second here, right? And so the idea is that today you should have already identified the questions you had trouble with. We'll straighten that out in office hours today, and then you'll finish it up tonight, submit before 11 p.m., and just make sure not to forget. Yeah, yes.
Attendance?
Yeah, I haven't started with the attendance yet. Yeah, attendance is going to start on Monday. Okay. It's just that class roster is still in flux, and we'll just wait till Monday. Yeah. So, by the way, I've been asked to let y'all know, I hope you've already noticed, but drop add is tomorrow. It comes up really fast in summers because everything is moving so fast. So anyway, just don't forget. Yeah. Okay, let me stop the recording and I'll stick around.